Hello. Hi guys, good morning. So basically this video we're going to see topological sort. You should forget what it is written, Kahn's algorithm. You don't know what it is, no worries, you don't need to know as of now or never, I should say. BFS, we will see why it is written, no worries, not sure, just see. We're going to see topological sort. Firstly, a few questions which you can practice by yourself after watching the video are these, and today we will see the topological sort. Now, before actually starting with this word itself, topological sort, oh, what does that mean? We will go at it later, but what is the use of it? It is the use when you have to perform your task in an order, which means if you have seen in the compilers or in the when your Java program builds or any program builds in general, any project builds in general, you have your maven dependencies, graded dependencies. You understand the word? A dependency, which means if the process A runs, when it gets completed, only then process B can start. When process A and C both runs, then only process B can start. When process B runs, then process D can start. When process B and E both have run, and process B internally would have started running when both A and C have run. It is that, okay, this process B has a dependency on process A and C. This process D has a dependency on both process A and E. This is what is called as being dependent on some other nodes, and this is called as resolving dependencies, and it is the most and the only important use of topological sort. Now, okay, you know that what this topological sort actually will do. It will help us to resolve dependencies. By this, I can actually figure out the dependencies itself. Now, just grab the same definition, same thing from the Google itself, because for sure this thing won't help us. Okay, we should know the proper definition of topological sort, but for your sake, a topological sort or a topological ordering, both are same because it's just ordering or sorting. Cool. Sorting is not the sorting in ascending or descending order, but it's like, okay, we have a particular ordering in which the nodes are written such that, okay, if as I showed you, to reflect this, to examine the same stuff, I will just write them in an order as A, C, B, E, D, which means anytime I look back, okay, if I have to evaluate D, which means all these will have been for sure evaluated, and internally I know, okay, to evaluate D, I would make sure that B and E would have been evaluated. So it is how ordering it means here. Now, cool, let's look at the definition just once. A topological ordering of a directed graph. Remember what? A directed graph. You saw what was happening. There were directions. My process B was dependent on A and C, not vice versa. Thus, it was a directed graph. Just make sure. Okay. Is a linear ordering. As you saw that, okay, I just made a linear ordering. Now, linear ordering of its vertices. Vertices are nothing but nodes, such that every directed edge UV from vertex U to vertex V, the ordering from vertex U to vertex V, U comes before V in the ordering. As we saw above, in this particular ordering, if we just write the ordering as A, C, B, E, D, then you will see A and B, A to B. So A comes before B. From A to B, from C to B, so C comes before B. From E to D, E comes before D. From B to D, B comes before D. It is the ordering such that, okay, if I just write the order down, then every node which is afterwards is only dependent upon maybe some of the nodes from the backwards. It is not vice versa. It can't happen that, okay, E might come afterwards, because actually E makes D dependent upon him. So basically E is to D. That is the reason E will come before D. It is what we finally need to obtain as an ordering. Okay, now you got to know what is topological sort, what is the use of topological sort in real life applications, and what this ordering in general means. Now, let's take the very most easiest generic example so that you can actually understand what it means. So with this example, if I just give you this graph and I ask you, by your human reading power, I'm not saying any mathematical things or any computer science things, by a human reading power, just let me know what is the topological ordering of this particular graph I made on the screen right for you. Pause the video and just make it, as I showed you above also. Now, after you just made it, let's see. Firstly, as we know, okay, the nodes afterwards are dependent upon the nodes which are backwards, right? So for sure, these nodes will come before these nodes. One thing you saw above also, right? Now, so what I can do is I can just write 2 and 6, right? After that, when it is written, after only that I can write 5, 0 and 3, which means after 2 I can write 5 and 3, after 6 I can write 0. That is what I mean. Okay, I can write 5, 0 and 3. Now, as 1 is dependent upon 5 and 0, so after 5 and 0 only I can write my 1. And as 4 is dependent upon 1, so after 1 I can write 4. It is one of the ordering. It's one of the ordering. Aryan, why one of the? Why not the only? It is because, let's say if I just replace 6 to, for sure, right? I just said that for 5 and 3, 2 should come before that. I never said that 6 should be dependent upon 5 or 3 or basically 2. I never said that 6 should come before 2 or 2 should come before 6. I never put a condition on that. So it can go anyways. It's just that the 2 should come before 5 and 3 and a 6 should come before 3. It is the only condition. That's the reason I can shuffle this. It's the reason I just made these buckets. Oh, now you can shuffle these buckets out. Although you can also go outside these buckets and do a shuffling, but it is just actually to make you show that, okay, there can be multiple possible ways that your topological ordering can be formed. You just have to find one such ordering. Okay, now you got to know what is the ordering and how you will actually make it. Cool. Because you know, these two nodes, which means the node right here and right here, are dependent upon the node 2. So node 2 should come first and then node 5 and 3. Node 6 should come first and then node 0. Then as 5 and 0 makes this 1 dependent upon him, so 1 is dependent upon 5 and 0, so 5 and 0 should come first and then node 0, like node 1. 3 and 1 should come first and then node 4. It is one such ordering. If I just replace these two, it is one such ordering. If I just shuffle these two, it is one such. It is one such. It is one such. So basically you can have multiple such ordering. Okay, now you got to know one thing. Now simple. Okay. Now you actually by a human mind can actually figure out, okay, what's the topological ordering, but it is not the human exam. It actually you have to code it. Now to code it, as we have been looking so far, when we learn the cycle in an undirected graph, cycle in a directed graph, anything like components, first thing comes in our mind is what we know in graph generally is a traversal algorithm. So by just a traversal, because a graph is just, okay, as soon as you hear the graph, just start traversing the graph. So okay, traverse the graph, and by traversing, is there any way I can find out what is the ordering? Okay, as soon as I hear the traversal word, first thing comes in my mind is BFS or a DFS. Now, many people I have seen on internet, they start with the DFS. It is the worst intuition of topological sort. To start the topological sort with DFS, it's the worst way to start with it, because it's no intuition at all to start with this. But we will start with the BFS. Why, Aryan? Why BFS? Okay, we know that to traverse a graph, we have this BFS and DFS. And I'm saying with both of this, it can be solved. But we'll actually start with the most intuitive form, which is BFS. Why BFS? If you just go back and clearly see what was happening, just see these two lines. What happened here? It is the first level you write down. It is the next level you just wrote down. It is the next level you just wrote down. It is the next level you just wrote down. It is what you did. At every level, if you just reflect this whole graph as this and as this. Now, you're just traversing every level by level by level by level. It is just a level order traversal. Level order traversal is nothing but a BFS. Breadth wise traversal. that is the reason I can, okay, for sure I can apply a BFS traversal, because I'm traversing level wise. I'm traversing level wise. And I want only this order, because see, in a BFS, you just traverse breadth wise, which means level wise, and you are only doing the same stuff. Thus, actually, we can use a BFS traversal for it. But now, how to do a standard BFS traversal? Can we apply that standard BFS traversal here, Aryan? Which means what I do is I just start from a node. I just push a node, any node I can push. I usually start from the node 0 to push. Then I will just start from this node 0. Then I push its child, which is this. Then I push its child, which is this. How come it is making sense that, okay, Aryan, because of your BFS traversal, you are starting from 0, because how usually BFS traversal work, you just push in the initial node. Initial node is usually a 0 node, so you push in the 0 node, and then you go on to the child of the node. Okay, you just go on to child, which is 1. So you will have in the topological sort, you will have a 0, and then you will have a 1, and then you will have a 4. Then maybe you will just go to any unvisited node which is not yet visited, which is, let's say, 2, and then you have to, hey, Aryan, just a second, is this the topological sort? Nah. Okay, I know one thing, I need to apply a BFS, but how? For a BFS, I need a start node to start from where to start itself. I can't blindly start from the node 0, because it may be at the mid, but I want from the start itself. Can you see something unique about these start nodes which are not there in these nodes? Can you see something unique? Something unique. In this start nodes, you have anything unique which you don't have in these nodes right here. See. You will see that these nodes have no in degree, no incoming edge. It has no incoming edge. No incoming edge actually means that they are the starting nodes, because if no one is starting behind me, if I am in a line and no one is behind me, then which means, okay, I am the last one to start, right? So they are the last ones, which means they are starting the graph itself. Thus. How to actually know? The in degree of them. And what Aryan in degree is, if you have not watched the starting videos, in degree is nothing but, okay, number of incoming edges to us. Thus, what we see that, okay, in degree of these two nodes are 0. But Aryan, okay, it actually by human eyes I can see that in degree is 0, but how to mathematically find, how to, in computer science we have to find that, okay, it's in degree 0. If you just go and look at this particular portion, see the graph, the adjacency list, it represents the node from U to V. U to V, mark words, to V, which means if I have a node 1. One node has 1 in degree from 0. Yeah, you can see from 0 it has 1 in degree. Node 4 has 1 in degree from node 1. Okay, yeah, it is there. Node 5 has 1 in degree from node 2. Yeah, it is there. Node 3 has 1 in degree from node 2. Yeah, it is there. So basically these are representing, okay, 1 has 1 in degree, I will just add a +1. 4 has 1 in degree, I will just add a +1. 5 has 1, 3 has 1. 4 again has 1 more in degree. Now its in degree is 2. It is empty. Its in degree is again 2, because it's again 1 was here and 1 was here. You can see 5 and 0. 5 and 0 both are going, which is making my in degree of 1 as 2, which means incoming edges are actually 2. Ultimately 0 in degree is 1, which means 0, where is the 0 gone? Yeah, 0 has only 1 incoming edge, so in degree is 1. In degree is nothing but incoming edges, and we choose, okay, V has actually what it represents, okay, it has the in degree as 0. And now you will see the only nodes which has in degree as 0 are node 2 and 6, because they were never updated because of this. Thus I can initially say, now I have to start from node 2 and 6. And how to find node 2 and 6? By just saying, okay, these two nodes have in degree as 0, so I will just start from these two nodes as in my queue. Now you will know, okay, I will start from the node 2 and 6, but now how to go? Okay, I just know this, they're in degree 0, so I will start from the node 2 and 6. But now in BFS we have a queue in which we push in the start node. Start nodes we push. Right now we know, okay, the start nodes I will push in will be actually the nodes with in degree 0, which means node 2 and 6. So I pushed it in my queue, node 2 and 6. Okay, node 2 and 6 are gone. Initially, I just marked all the in degrees, and now, okay, I just did, okay, it's actually, okay, we can obtain this topological sort, but initially I marked all these in degrees. Now, actually the queue part starts, which means the interesting part starts. Firstly, I will just push in these two nodes, which means 2 and 6 in my queue. Now, when 2 and 6 are gone, what happens in a BFS? You just push in the node, then you push in its childs. But can I blindly push in its childs? Which means, okay, if I just land at 2, then can I push in a 5 directly? Maybe, maybe not. Why I'm saying maybe not? Which means if it had been the case that 6 points to 5, okay, we will see it later, but actually I will show you. Okay, if we have a node, let's say 6 points to 5, okay, if 2 has been done, 2 is gone. Can I push in 5 right now? Why? For that, 6 also needs to go. Thus, only when, okay, now it is done, which means, see, as I said, a topological sort is then when your past, like older things, which means previous things, when they have been solved entirely, only then I can start solving myself. Earlier we saw that 5 was dependent upon both 2 and 6. Thus, when both 2 and 6 have been gone out of my queue, only then I can push in my 5. So right now I can't. So basically for this case, my 2 had, I was starting from 2, then basically the 2 has gone. So now maybe I can push in the 5. That is what we have to keep on thinking while pushing in the BFS. It's the only difference between a BFS and a topological sort. In a BFS, you stand onto a node, then you can push in your childs. But in a topological sort, before pushing on your child, you have to check, okay, has my child's all the parents have been resolved or not? If all the parents of my child are resolved, then only I can push in my child, else I cannot. Sorry. Thus, let's start with the queue itself, of standard BFS itself. Firstly, I will push in my 2 and 6, as you know. Then firstly, as 2 and 6 are gone, okay, then it will just go on in my topological sort thing. Okay, vector, I can make a new vector or something, I can print them, I can do whatever I want. Okay, 2 and 6 are right now with me. Now, as both 2 and 6 are gone, which means these edges because of 2 and 6 are also gone. So basically incoming edges, which means in degree of all these nodes will reduce by 1 because all of them were having 1 edges. So you will see in degree of 0 reduced by 1, in degree of 3 reduced by 1, in degree of 5 also reduced by 1. Thus, I can just, okay, now in this step I can see in degree is 0, 0, 0. Now, it is the new stage of the graph, new look. Just have a new look at the graph, right? Now, all this is gone, all this is gone. It is the new look, which means I will now have in my queue 5, 3 and 0. So now, in the next step, what will happen? 2 and 6 were already in my sorting. I have already printed the topological sort. Then comes our 5, 3 and 0, or you can also print 5, 0, 3, you can print anything you want. It is just, okay, these 3 will come in the picture. Now, when these 3 would be going, then what they will do? Okay, if the 3 will go, then 3 will reduce the in degree of 4 by 1, only by 1, because 3 has only 1 edge to 4. So it will reduce my in degree of 4 by 1. Still, it will have, 4 will have 1 in degree remaining. My 5, as it goes on, so it just reduce its 1's in degree by 1. Okay, 5 reduced its 1 in degree by 1. 0, it also reduces 1's in degree by 1. In the next step, you will see 1's in degree has now become 0. So the new graph is something like this, which means my topological sort so far is a 2, 6, 5, 3 and 0. Now the new graph looks something like this, with 1 as the new node because it has in degree as 0. Now I will just push in this one. Now, okay, because of this one, as this one has been pushed, now because of this one, as it goes out, it goes out. So it will just reduce the in degree of 4 by, it was already 1. So now it will get reduced to 0. The in degree of 4 got reduced to 0. Thus, I will just push in the 4 also. So basically earlier 1 got, after this 0, 1 got in my sorting and then 4 got. So now this is the topological sort. Thus, you will see that you obtained, okay, last comes 4, and after the 4 is gone, okay, it is also is gone. So entire thing is gone. The queue is empty finally, and you would return your answer. You will see that what you got. You got your topological sort. It is what you have to do. The only difference between a standard BFS and a topological sort is that you will start, okay, the node to start from, you will choose by seeing the node having in degree as 0, and to actually, when you are actually completed your root node, but you have to push in your child. You can't push in your child blindly. You can only push in your child only and only when all of its parents have been visited. As you saw here, when I did, where is the graph gone? When I did remove my 5, 0 and 3, I removed this edge, but now I cannot push in my 4. I can only push in my 4 when all its parents, which means 1 and 3, both are gone, but 1 was not gone. Thus, I could not push in my 4. I only push my 1 because all of its parents were gone. That is what I'm going to show you. Cool. So it is what you have to do. That it's actually standard BFS, which you have to do. Now, see. Let's go into the code. It's very, very, very easy. It's exactly the same what we have seen so far. Firstly, I will have the in degree because I know I need to maintain an in degree. Why? I need to know the starting nodes, what to actually start from, and also I need to know, okay, at a point of time, if all the parents are resolved, which means every point of time, I'll just keep on reducing the in degree. I'll show you later, but yeah, in degree is needed to just check, okay, if all the parents are gone or not. So I'm just getting this in degree. In degree is nothing but if it is the node from U to V. So basically V, which means node to neighbor. So neighbors in degree will get increased by 1. You will see I'm just going on to the node, and then at every node I'm just going on to the neighbor of that node, and then that in degree of the neighbors got increased because the node is from node to neighbor. That is the reason. Cool. Now I just push in the nodes. What nodes? The nodes having in degree as 0. Only those nodes I can push in my queue. It is standard BFS I'm gonna show you. Now comes our standard BFS. If you have not watched the BFS video, just go and watch. But it's a standard BFS that you use a queue. It is the answer, which is the topological sort. I used a simple queue, which is mentioned here. Now until the queue is empty, as we do, we grab the size because we want to traverse layer by layer. So we just grab the size so that we can iterate on the entire layer once. Thus, I just grab the size to it on the entire layer once. I just go on to this layer, and at every step, I'm just grabbing the node. I am just pushing that node in my topological sort ordering because it is the ordering I need to return in the last itself, right? Cool. Now, as I evaluate this node, so I need to make sure, okay, for this node, whosoever child was there, as this node is going, bye bye, tata, goodbye. So I have to reduce the in degree of all its neighbors. So I am just going on to the neighbor of my node, and I'm reducing the in degree of every of the neighbor because I am going, the parent is going, so the child's 1 edge is also going. While in the case it can happen that, okay, it is a node and it is some other node, let's say U. Okay, it was having some of the edges like this. The node is having edges like this, while this node U was having the edge like this also. So as this node was going, okay, cool, tata, bye, goodbye. But still you will see that you can only push in the queue only these two nodes, not these two nodes, not these two nodes. Why? They still have a dependency back with them. So they can't go in the queue. But these are free, these are empty, these are blah, blah. So they can actually push in the queue. Thus I will check, okay, if the in degree has reached 0, then only I can push in the queue. Thus I will just say, okay, just push in the queue. And ultimately it just goes on. The loop goes on. Simple BFS, just that pushing condition is depending upon the in degree itself. That's it. That is the only change in a simple BFS and this thing. Then ultimately I can just hit in the topological sort. Now the complexity is nothing but simple V plus C, which is the standard complexity of doing a BFS traversal. You go on to every node and every edge to actually find the answer. Space is nothing but O of V itself because you are using an in degree and a Q. Now. Before going on to the, okay, it is done. You will think it is done, but you should remember one thing. You were able to solve on this particular graph. You know one thing about this graph. Firstly, this graph is directed. Okay, it is directed. But it was also acyclic, which means it had no cycle at all. But Aryan, why cycle is important? which means why it is important that it should not have a cycle. See, if it would have a cycle, then at a point of time it would have come that none of these nodes would go in my queue. Why it would not go in my queue? Because you remember the condition. To go in my queue itself, I had a condition that in degree should be 0. And you will see all these are dependent upon each other. Which means in degree of this is 1, in degree of this is 1, in degree of this is 1. No matter what, in degree is not going to change of anyone. So none of these will go inside the queue. Which means none of these will actually reflect in my topological sort. Thus, it is important that if you are finding the topological sort of a graph, it should actually be acyclic. Which means it should not have a cycle. Which means a directed graph should not have a cycle. Which means it should be a directed acyclic graph. Thus you will say, Aryan, oh, so is it meaning that we have to firstly make sure that a directed graph is not having a cycle? Which means I have to firstly find out that if a directed graph is having a cycle or not. Is this I'm gonna find out? I will say that although in the problem itself, if it just says you, okay, just return the topological sort of this, and if the answer can't be possible, return a -1. For sure, you have to first make sure that it is not a topological sort. But Aryan, so in the last video, in the last lecture, as it is the lecture number 16. So in the last lecture number 15, we saw how to find the cycle in a directed graph. So I have to apply the algorithm, that one first and then this one. I'll say no. There's a sweet hack for this. You just have to use the same algorithm, and ultimately it will just show you that okay, it is having a cycle. You don't have to do it. Which means with this topological sort itself, the algorithm right here itself, you can actually find if the directed graph is having a cycle or not. And thus, in the next video we will see how by this topological sort we can actually find the cycle. But it is that you should make sure that okay, a topological sort, it works on every graph, but the correct answer for this graph would be find out only when the graph is acyclic, directed acyclic. Cool. Now, okay, you learned this, but now to practice the question, it is one of the best question you can find, because see, other question you actually know that okay, it is being applied. In this question, I actually showed you, just write on Google, if you see, if although the link would be down below also, but if still I forget to write the link down below, just write on Google, largest color value in a directed graph by Aryan Mittal. You will find this video at the top and just watch this video. See, in this, I from scratch told you that, okay, we know this thing called as topological sort, but out of the standard problem of course schedule 1, course schedule 2, we don't know where to apply this. Thus, it will actually be seen that okay, how you actually apply these kind of sorting thing in actual problems. Thus, I highly recommend to just go and solve this problem. If not, then you can just go and watch this video itself. Code for C++ and Java, exactly what I showed you is down below. Just bookmark this, just add this as a snippet, because it will be very useful. Cool. In the next video, we will see how to find the cycle like with the help of this topological sort. And in the next video of that, we will see how to find topological sort via the BFS. Although it is the most unintuitive way, and I will highly recommend in exams, in practicals, in your interviews, just solve it by the BFS, because it is what you will remember also. It is the most intuitive thing, because it is the most intuitive thing. It is not that intuitive at all, but still I will just show you the intuition behind it, but it is not very intuitive, I should say. Cool. That is all from me. See you in the next video. Take care. Bye.